In this video, we'll define a signal, showing some examples, proposal of classification of signals, and how to operate on them. What is a signal? A signal is the recording of a set of physical variables that here are called with the letter X. With respect to other physical variables, we are called with the letter M. The number of recorded variables is the number of channels of a signal. The number of independent variables is the dimension of the signal. Most of the signals are continuous with respect to the independent variables. Here is one example. So this is an electrocardiogram of a person, and we have 4 electrodes connected to the body of the person. So we have a 4-channel signal. All these variables depend on time, so it's one-dimensional. Another example could be the output of a loudspeaker. So it's showing the pressure in the air produced by the membrane of the loudspeaker. And here we have 1 channel, which is the pressure, with respect to time, which is the independent variable. So from here to the end, I will always use examples with 1 channel and 1 dimension for sake of simplicity. And this 1 dimension will be time. So from here, the signal will be X dependent of time. Just a note, it's trivial, but it's better to remember. If you have the time axis, the positive part of the time axis is the future, so it's second from now. The time 0 is now, and the time less than 0 is the past, seconds ago. So the unit of the time axis will be seconds. One kind of classifying the signals is depending on the value of the variable x. If x is an integer, you have a signal which is a signal of integers, for example, the population of a city, or it can be real, for example, the output of the loudspeaker. So in the second case, the variable x is a real number. Another kind of classification is saying the signal is complex. It means that the variable x is a complex number, and you have to produce 2 outputs, two channels. It could be the absolute value and the phase, or it could be the real part and the imaginary part. So you can think of the complex signal like a 2-channel example with the independent variable being the time. Another example depends on the continuity of the time axis. If you have the signal defined for every time, you say the signal is analog or continuous, or you can have the other kind of signal which is discrete. It means that you have a sampled version of the continuous signal. Usually the discrete signal is produced by sampling the continuous one with a constant time step, capital T, so that you convert the continuous signal into a table of numbers. I have a slide now showing what is the advantage of using discrete signals. So in the discrete signal presentation, all the signals are converted to tables of numbers. And with numbers, it's very easy to do the processing. With numbers, you have a stability of the result, because if you don't lose, if you don't miss one of these numbers, you are conserving the information you get in the signal. And you need only a single hardware to process the discrete signal, which is ideally a computer. You see an example of a continuous and a discrete signal. The continuous one is represented by the audio tape. The discrete one is presented by the musical sheet. So every time you use the audio tape, you produce a different kind of signal. You introduce some error. You destroy the support. Every time you use the music sheet, you play the same music. So the only advantage that remains now in the analog signal maybe could be the speed. Let's go back to the signal. So you can define the shifting along the time axis. So if you replace t by t minus tau or t plus tau, you're moving the time axis, or you're moving the signal along the time axis. If you think that tau is like a positive number, if you do t minus tau, you are moving the signal to the future, so it means you are delaying the signal. it will happen in a different time from some seconds from now. If you do t plus tau, you're moving the signal to the past, so you're anticipating the signal. What happens if you, instead of adding or subtracting a quantity, you multiply the time axis, so you are expanding or compressing the signal depending on the absolute value of the factor A multiplying the time axis. If A is less than 1, you are expanding the signal. If A is bigger than 1, you are compressing the signal. Plus, if you have a minus, you are reversing the signal with respect to the y-axis. We are defining also what is a periodic signal. A periodic signal is the one that repeats itself every t0 seconds. T0 is the period. You can think of the periodic signal like the repetition from minus infinite to plus infinite of one period delayed by an integer quantity of periods. So if x of t is, in this case, not the whole signal, but just one period, the y of t periodic signal is the summation, overlapping of many of these periods delayed by one period each with respect to the other. Let's see some operation on signals. So you can sum two signals, and in this case, you are overlapping one over the other. So for every time, the summation is the summation of the values of each one of the two signals. And so the two signals are overlapping one on the other. The multiplication is for each time, you are doing the multiplication of one value of one signal from the same value of the other signal. Suppose one of the two signals is just zeros or 1. By doing the multiplication, it's like opening or closing a window on the observed signal. So it's sometimes called windowing operation. One of the two signals is switching on and off the other by being 0 or 1. Finally, another way of looking at signals is to compute their energy or their power. The energy is defined like the integral of the signal square. So you have always a real number and positive. Every time you move away from 0, you have to spend energy, so it doesn't matter if this is negative or positive, you do the square, so the energy is always positive. For some signals, it's not possible to define the energy because they are always on. Think of the noise. And so you can, instead of expressing the energy, which is infinite, you can speak about the energy per unit time, which is the power. So these are called power signals and apply to signals that usually have a non-finite duration, while you speak of energy for the signals that have a finite duration. They could be, for example, the wavelet representing a bit in a flow of bits, or the finite duration wavelet. For the periodic signals, they have infinite energy, but you can define the power like the power of a single period.